Hello and a warm welcome back to my channel. This is perhaps the last video you need to use before you commence your internal assessment. Throw your test tubes in the bin, throw away your requisitions for chemicals, and just see the light about how much more simple, more easy, and how successful it is to use secondary data for your internal assessment in IB chemistry. Why do I make this video? Because my mind has changed massively over the last 2 years. 2 years ago, I made this little video here on the right-hand side of the screen. How to smash your IA, the pandemic edition. Thank you, everybody. I'm very grateful for the wonderful amounts of views. It's somewhere around 17,000 views, something I never thought would ever be possible. I'm very grateful for that. Thank you again. But things have moved on in the last 2 years for me, for chemistry, and for the world, as we all know. So I'm making this video as an update, giving you some actual train lines along which you can run your train and get to the village of success at the end of your IB journey. Who is this for? This is for students and their wonderful teachers, and perhaps it will stimulate some further investigations and some further questions with details at the end of this presentation that you can use to contact me directly. What do you need to know now? Not a great deal. Hopefully you have done your IB chemistry learning, teaching, and you have a good grounding in your standard or higher level chemistry. Remember, there is no delineation between standard and higher level in IB chemistry internal assessment. Yes, this will be the last year of IA as it stands, but to be fair, the changes are very minimal for the next iteration. As I said in a post recently, it is more nuance than paradigm shift. So, I'm sure you all have watched that video. There's some good advice in there. Very good. What we're going to look at today? Well, first of all, I want to look at how can you hit the top bands. It seems monstrously difficult to get personal engagement, exploration, analysis, evaluation. Just about every aspect seems so much more difficult with secondary data. But is it? I want you to show you how to get some excellent ideas. I will be joined by a colleague. The IB is supposed to be collaborative, and I will introduce her shortly. We also look at chemistry at home. Previously, I have said, do not do chemistry at home. The risks are too high. However, I reserve the right to change my mind. My mind has changed. I think there are a number of areas that we can use safely, and that's the key for chemistry at home. We also want to be able to use databases, simulations, and modelling software. I have separate videos on my channel of how to use those. The risks associated with doing a secondary data internal assessment are well known. It seems, apparently, much more difficult to hit any of the criteria than it did with the old test tube, burette, pipette, lab approach. Personal engagement. How do we demonstrate personal engagements? We need to have at least around about 10 sources. No one says these words, these numbers. They're not there in the criteria. But if I want to feel like a student cares about what they've done, and to a decent level, I want to see around about 10 plus academic references. I want to see reflection throughout. I tried SDBS Spectral Chemical Database, but pentan-2-one was missing from the consideration, so I had to use NIST instead. This honest reflection and truthful recount of the journey, and the internal assessment is a journey that the student has taken, is what will push it to the top bands. Varieties of sources and authentic presentation. Every student does a trial, whether it's primary or secondary. I'm working with some students right now. They're trialing the bottom, middle, and top of their dependent variable to check that there's actually a trend. Because this is so open-ended, there is a whole almost infinite possibility of research questions which you can do, which we couldn't previously dream of doing. Exploration. Do not be limited by one dependent variable. Use two if they are related. Try and get some relationship between the two dependent variables, but keep the independent variable to one. Okay. How do you control variables in the method? How do you say you've controlled your variables? Well, you say what did and what didn't work. You say why you chose what you chose. You say why you chose to study what you chose to study. You say why each source was included, and as important as I've said, which was discounted. Why did you choose that range of the independent variable? Why did you stop at dodecane? Why did you begin at methyl ethanoate, for instance? The chemistry, just to emphasize, the chemistry has to be IB level chemistry, and lots of it. If it's just lots of words on the page, talking about irrelevant things, that's the same for primary and for secondary. Okay, we care about the chemistry. Analysis. This gets a bit easier, I would argue, for secondary data. The units are there. The uncertainties can be dealt with in a number of ways. We can have the uncertainty of the last decimal place. Okay, we can find two different sources, particularly if you're looking up databases with thermodynamic data, enthalpy formation, combustion, entropy, whichever molar enthalpy you can think of. Every one of those can be augmented by doing an average bond enthalpy calculation, or an enthalpy of formation data calculation, or an enthalpy of combustion data calculation. So you're trying to get the database value, something to compare it with. And when you've got the two values, do the half range, halfway in between the medium value, and that will be plus or minus that value, whatever it is, for half the range for each of your data points. And you're already hitting the top bands. That's perfect. Okay. Highlight your anomalies and talk about any variation in your control variables, because if you are taking database information and you are calculating it yourself, the conditions will undoubtedly be different. Check the conditions in the data booklet, what they used, and check the conditions within the package or the database that you're using, and talk about that. That was an uncontrolled variable. An uncontrolled variable is just as valuable as a controlled variable. It shows that you understand the experiment and the limitations of your experiment. How do you solve the problems of absences of data? Well, you can extrapolate to an extent. It's always better to calculate before you extrapolate. Explain, be aware of it. Don't try and hide it. Your moderator will see it. Try and explain why that missing data is missing. Is it such an unusual exotic compound that the standard free, and that's what we're after here, free simulations, databases and modeling sites are unable to give the data that you need? If that's so, why did you pursue with the research question is another valid question to ask. Wherever possible, your analysis must be more than raw data. Just reading bond angles, just reading melting points is not enough. A unit conversion is going a long way towards addressing that manipulation or calculation expectation in IB chemistry. So converting Hartree units to kilojoules per mole, converting angstroms to nanometers. All of these you can build a spreadsheet and get it to do it for you. Again, a separate video on my channel of how to do that. But analysis, again, I would strongly suggest is easier using secondary than with primary. Evaluation, we still need our systematic and our random errors and our R-squared values and our error bars. Our error bars would come from last decimal place, half range method. You may even, if you've got more than 30 pieces of data, which is perfectly possible with secondary, standard deviation then becomes legitimate as a tool to assess the errors. R-squared is always brilliant, but not just put in. You need to discuss it. What's the degree of correlation? And wherever possible, find a literature value. Okay, no matter how dimly or tenuously related, find it, talk about the differences, talk about why it's different, why it's the same, why it's significant, why it's not significant. And then throughout, what we're looking for is always chemistry. Because where do we begin? I begin by showing them around WebMO, video here on my channel, ChemReacts and ChemCollective, and ensuring they have a very good understanding of how to build spreadsheets. We also have 4 documents here, which I will click into. I would love to hand over now to the wonderful Miss Kathleen Quinn, a fellow chemistry teacher, out of Qatar. Over to you, Kathleen.
Thank you, Mr. M. I'm honoured to be asked to contribute to one of these fantastic videos, which have helped me a lot. And really, I had this document before, and it really helped me refine this document this year. So why did I make the document? There really are two reasons. The first reason being that students don't know how to project manage. They don't know how to break a research project down into bite-sized chunks, into interim deadlines. So I found that by doing that, fewer students ended up at the data collection point with no idea about what they were doing, because we'd been able to intervene at various stages before that. So I do it using a tracker, which looks like this. My dates are there, which correspond to the planning sections in the document. It would look different in different schools depending on whether or not you devote 2 whole weeks to it, or if you're doing it in between teaching content. But ultimately, when it gets to this day for the IEA data collection day, I need all the students to be at that point. They may not all be, but designing it this way has certainly helped with that. Second main reason for this document was really fleshing out the introductory part, the topic choice, because what I've realised over the years is this is key. A lot of the problems that arise later in the process with the process data and then the analysis and evaluation section, it actually stems from a poor choice of topic and research question at the start. So this is essential, and this is what the Mr. M videos I think are really helpful with. So within that, I extended this part of the planning document to include Mr. M's video on the awesome ideas, and I'll put the database and home chemistry ones in there also. Having another teacher voice, someone that they know is a moderator, someone that they know is expert, and this goes to you too, students, if you're watching this video, really helps. You know, students will take some parts from us, but often it helps if there's another source saying exactly the same thing, but perhaps just in a different way. So using this to come up with good ideas really helped the process for me this year. The way that I kind of fleshed it out with the students was by having them think of these key questions before they were able to generate a research question. So making notes using these questions below for different topics, and then at the end actually filling in a Google form that asks them to answer a lot of these questions. Often students will say, I want to investigate this independent variable, and they use terms like the effectiveness or something else for the dependent variable, and it's sort of saying, no, what exactly are you going to measure? And often they're not aware of that, and they have to research the methodologies that they might use and how they might measure the effectiveness of something. So it's just to really get them thinking about that from the get-go, because I think that having a key idea at the beginning of how the investigation is going to go really helps solve a lot of the problems that arise later, as I said, in the analysis and evaluation section. Just to tie it up and make sure there's no escaping them answering those questions or ignoring the questions, I usually do a Google form that asks them to answer all of these questions in the Google form. So they really have to think about it. If they can't answer the question, they have to go do research to find the answers to those questions. Or if there's no answer to that question, or the answer is no, then they have to find a new topic. So that's the main reason behind this document. I hope it's helpful. Feedback is always welcome on how it could be improved, or reshare documents that perhaps you've done and I can adapt and add in, because I think we're all still learning within this process. So thank you, Mr. M, and it's back to you.
The inquiry process for me starts with the wonderful checklist and planning template which Kathleen Quinn authored, and thankfully, gratefully to her, she just explained. I also get the kids to watch my videos, gives me views, it's good. Look at the syllabus, they're on the right hand side. But for getting them off the nursery slopes onto the hills, then we're looking at giving this scaffold. So the research question we don't want them to hold on to for dear life and never change it. It is a changeable, evolving thing, the research question, never refined until you've done your evaluation and conclusion. I give them examples of great, weak, and complex, overly complex research questions. And then I tell them what's the effect of increasing the carbon chain length of the, insert your class here, on the strain energy, or you can subdivide the strain energy into bond, stretch, angle, bend, OP, bend, torsion, van der Waals, electrostatic forces of attraction, etc. And then augment that with the John Chewies site, and they can choose whichever one that floats their boat. They could use these things, okay? They have to build a spreadsheet, they have to do their uncertainties, and they have to submit the graph in a full IA. What can we do at home? Yes, 2 years ago, I said, under no circumstances would I allow students to take any materials home or to do any chemistry in the home environment. The risk of a smaller child or sibling drinking some dilute sulfuric acid would keep me awake at night and cause even more hair loss on my rapidly aging head. So, what's changed my mind? Well, with a very narrow scope of risk, i.e. no more risk than is present in the household, I have found a number of things which I think will be viable as a home-based internal assessment. One of the great sources that I use is the Journal of Chemical Education on the right-hand side, these guys here. Now, not everything is free. I only use the free things myself, and it does take a little bit of trawling through to find which ones are without cost. This is one, and this is categorization of quantum dots, clusters, nanoclusters, and nanodots. Show me a student that's not going to be excited by that title. When you investigate, and there are many videos on YouTube about how to actually make this happen, you need nothing more than a common fruit, strawberries, lemons, durian, wherever you are, and you can make these in a microwave oven at home. They do have properties which are quite stunning, quite startling. They will be fluorescing, if that's the correct word. They will glow in the dark. I'll keep it simple. They will glow in the dark if you make them correctly. And you can categorize them at home very simply. Follow Journal of Chemical Education and see what you can find. This one for me is a goer. Graphene. Graphene is that wonder material which has been much lauded for probably over a decade now, probably a couple of decades, because of its properties which every IB student will know. And it's sp2, 3 bonds, 3 electron domains, it's trigonal planar, exists in sheets, can conduct electricity, etc., etc. An IB kid will be all over this. But how do you make it? You can make it in your kitchen with soap and a blender. I see no real risk associated with this, and I can see a student making some, looking at conductivity, doing some calculations, and showing how they actually prove that they synthesized some graphene at home. I think that sounds great. Alcohol from paper. This one is about making, it's almost like a prison video, where you can actually make your own alcohol using toilet paper. Nile Red, I'm sure you're all familiar with. I don't know the chap. He's got way more subscribers than me. While we're talking, click that subscribe button. But here, it gives you a step-by-step method, as well as many other less safe methods of how to make toilet paper moonshine, as is the title for the video. A student could make this. They could look at MC delta T, they could compare that with the average bond enthalpy calculation from the data booklet, augment the data. We're always looking to augment the data with a secondary or even a third source. That would be fantastic. And then you've got the idea of range. You've got your uncertainty. Bish, bash, bosh. Beautiful. Ferrofluid. What do I need to make ferrofluid? Well, apparently, according to this, you need some vegetable oil, some iron filings, some napkins, and a magnet. Great. Well, why would you make it? Well, first of all, it's fun to do. Second of all, we can look at perhaps different properties of the solvent in which it is in, different oils. We can look at different behaviors. We can perhaps get the period of oscillation. You know, the ideas just seem to flow forwards on this one about how we could change that into an internal assessment. I can't give you specific research questions. That would be breaking the rules. Glow-in-the-dark liquids. Richard Thornley, bless Richard, has got a wonderful video on his channel about activation energy using glow sticks. But if you don't want to have the risk of broken glass on your students or on yourself, then all you need is a plastic bottle, some isopropyl alcohol, which is propan-2-ol, you can buy that from any chemist, and a chlorinating tablet for diapers, babies' things, or for a swimming pool. And then allegedly, according to this, we have a glow stick. You can use your cell phone, get the colorimeter app on your cell phone, look at the colour over time. You can do some rate of reaction. Again, there's a video on my channel about how to change that light intensity data into a rate to get the rate constant, do an Arrhenius, and get the activation energy of any homemade glow stick. Maybe a bit too much information there. The smartphone, let's stop calling it, my little mission now, a phone. It's not a phone. How many phone calls do you receive a day on this thing? And how many other tasks do you do? It's a computer. And this little computer, I already have it open, sorry. This little computer in every student's hand, here's the Journal of Chemical Education again, has such massive potential to be used. Light meters, brilliant. Red, green, blue, quantitative measures of the spectrum as a reaction is going on at home. Build a spreadsheet, plot a graph, do your uncertainties, top scoring, IA, no problem. And Briggs-Rauscher reactions. I'm perhaps scraping the bottom of the barrel here from the safety point of view. Yes, Briggs-Rauscher, you do need to have a bit of acid, you do need malonic acid, you do need some manganese sulfate. But in all honesty, there's nothing more dangerous than what we would find in the kitchen sink in terms of lye and drain cleaners and bleachers and that sort of thing. And how many kids cannot be mesmerized by the magic of a Briggs-Rauscher reaction? Follow it using your phone, follow it using the timer, get the rate of reaction, Arrhenius, off you go. So, within a narrow band of careful risk management, I would suggest that the home laboratory is a viable option if your laboratory at school is closed. PhoneBased Chemistry. Yes, it's not a phone, it's a computer. I have this video at the bottom. This chap here, this crazy boy down at the corner here, has a video on his channel about how to use this little computer you've all paid $1,000 for to follow a reaction. It gives you all the ingredients, even gets this large chap here talking about things that's going on with the chemistry. Underneath the video is also a sheet that you can use. There's a picture of my old phone. I've got a new one now. My old phone down there. And what it allows you to do is to create this little spreadsheet here. There is some calibration to do. Yes, calibration is part of your control variables. Time interval, reciprocal of time, absorbance, natural log of absorbance. Here, this is how to calculate the absorbance. This is first order kinetics. This is second order kinetics. And whichever one gives you an R-squared value, the closest to first or second order, will give you the order of the reaction. This should be mushrooming into lots of ideas. Okay, yes, there's hydrogen peroxide and blue dye. Hydrogen peroxide you can buy at the chemist or the hairdressers. Blue dye is in the food aisle underneath cooking. Okay, but you can also use it for fermentation. You can use it for anything where a colour changes. If you think of a reaction where a colour changes, you can use this method to get orders of reaction. High scoring IA, boom. This will be your guaranteed route to success. There are many databases which we can use. I've HUP, and I guess that all and sundry have heard of NIST, ChemSpider, PubChem, and SDBS. I'll show you them briefly if you have not seen them. Don't worry. John Chewie, very highly respected person, probably the #1 person for internal assessment on planet Earth. You'll hear me saying that, but respect is due, John. Has built using his knowledge of Python and of programming to build this beautiful website here. So when I'm guiding students, the first thing is that I show them two things. I make sure they're competent in doing two things. First thing, I make sure they can navigate and use John's fabulous website here. So this harvests data from PubChem, which is here and well used and well known by teachers around the world. And Thermo. Thermo's a package which does have a paid side to it, but does do calculations, and it harvests from these sites the data which is presented before us. Because how many times does a student begin a database IA and there are big gaps within the IA because they can't find the enthalpy of formation or the entropy value or the molar enthalpy of fusion for some exotic, I don't know, ester which they've been looking at. Well, here is the solution, and I can type into here any chemical that I wish and double click it. Then we will hopefully find, just double tap, that we've actually got, methyl ethanoate here. We've got the synonyms, general properties, but I'll start from the bottom and work from the top. Okay, so we've got the standard state absolute molar entropy and the absolute molar entropy in an ideal gas state. Okay, well, how is that useful? Well, they're in two different environments, in two different physical conditions, but within the same ballpark. We can do a half-range method and get the uncertainty. We're always thinking about the uncertainty on there. Enthalpy of combustion for gas, enthalpy of combustion higher and lower. This is from different sites. So again, you've got half-range method. In between these two is the uncertainty. That problem of having no uncertainty for secondary data evaporates. Phase transitions. We don't do these massively at IB, but this means they're a great thing to explore for internal assessment. Vaporization, sublimation, and fusion. We've got the things that the kids will be familiar with, enthalpies of formation, but now we've got it for gases. And we've got the Gibbs energy, Gibbs free energy, and entropy for a gas and molar entropy of formation. Again, halfway range method for uncertainty between these values. You're off to a high scoring IA. Critical points, kids can understand critical points. Supercritical fluids be a great thing to include above and beyond the syllabus. Log P, the solubility in octanol compared with water to mimic the blood-brain barrier. One of my students did that 2 years ago now. Surface tension, link that with Van der Waals forces, show you how to get those shortly. Phase transitions, vapor pressures, melting points, triple points, flash points, just goes on and on and on. It's an absolute boon for us as people trying to get high scoring IAs for our lovely students, and for you lovely students trying to get high scoring IAs. Here are the Van der Waals volumes in the Van der Waals area. Okay, what use is that? Well, ting that with WebMo, I'll give you a quick tour of that in a second, and you're off. Okay, so you can put any chemical into here and look at all these thermodynamic properties using John's site. You can also change the temperature and the pressure. What's the effect of changing the temperature on the molar enthalpy of fusion of a series of esters? Boom. That's a great research question. I promise not to give you a research question. But this is just infinite in the possibilities that it gives us as students and as teachers to explore. But the first thing, that's the second thing I show students. The first thing I show them and make sure they are familiar with is, of course, good old WebMo. Yes, I have videos on my channel to do with WebMo. There are many other videos on people's different channels. So you saw the scaffold which I give to students for their first secondary data IA. What's the effect of insert class here? So a student could be looking at, I'll just make this as I go along here. They could be looking at the carboxylic acids. Okay, so double bond to the oxygen, single bond to this oxygen. Clean up, and we'll go for mechanics. Okay. Just a note, if you go to idealized, that will go as the textbook, so go to mechanics. Okay, now we have a beautiful molecule of ethanoic acid, as we know and love it. A great teaching tool as well, as you can see. Our sp3 tetrahedral here, sp2 trigonal planar here, 2 lone pairs of electrons in each of these. This is V-shaped bent hybridization. Also sp3, excellent. Well, what use is it? Well, I hit my pointing tool, I hit 1 and I get hybridization. I hit 2 and I hit bond length. Whatever is highlighted, I can adjust. So now I can adjust the bond length. It's currently in angstroms 1.519. Okay, I could make that 3. Let's double the bond length. Watch what happens. I've doubled the bond length. But what's the point of that? Why would I want to do that? Undo, let's go back. Because this button here, our calculate button, is a quick 2-second, boom. What have I got? Total energy of the molecule in kilocalories per mole. Not an IB unit, but kilojoules per mole is an IB unit. And if we go kcal per mole to kj per mole, then we'll find that I think it's 4.164 to trigger happy on the click. 4.184, beg your pardon. Okay. We've also got van der Waals forces. Oh, van der Waals forces here in kilocalories per mole of this molecule. So I can look at a sequence of carboxylic acids, esters, aldehydes, ketones, amides, amines, insert your class here. And of course, it's secondary data IA, so I can go up to 30, 40, 50 carbon atoms long and look at the effect on the van der Waals radius calculated here within WebMo, compare it with here within John Chewies' website. And again, that is a clear path to a wonderful uncertainty treatment. And this just allows me to explore things I could never ever believe would be possible for a high school student doing their IB in chemistry. I mean, yes, build a molecule in here, look it up in here. That is just, wow, that blew me away when I realized that that's, every kid has a different research question when I do that. Of course, there are other things in here. If you've already done spectroscopy, you can look into SDBS, agree to the disclaimer. You can go into here, get the MSIR, carbon-13 NMR, proton NMR, for any compound that you can think of. And critically, within WebMo, just show you this here, there we go. Within WebMo, I can look it up and go to databases. And then here within WebMo, I already have the key databases, NIST, PubChem, ChemSpider, NMR Shift DB, and SDBS spectral database at my fingertips. And I can just flick into ChemSpider straight from, thank you for that. Usually can flick into ChemSpider straight from there. Maybe because it's highlighted. Let's try that one again. Look up databases, ChemSpider. Behave, please. Send anyway. It's my firewall. Come on, you can do it. Come back in there. I have it open here. Your firewall will be less sophisticated than mine. So you can go straight into ChemSpider. You can put your name into here, search it, and you're off. NIST is the same. NIST has been used by so many students in the past for wonderful database IAs. Look on the IB teacher support material. You need to play with these things quite a lot to get used to them, more than I've got time to do here. But, NIST, ChemSpider, PubChem, SDBS, a little bit. Students use a little bit. WebMo and John Chewies' site, together with some decent chemistry, great error treatment, wonderful graphs. You can do some chemistry, which is just above and beyond anything I've ever seen. When a student has got to grips with WebMo and John Chewies' site, what sort of research questions does this stimulate? This is a live sheet from my classes, which I'm currently teaching, and we'll pluck a few at random. Let's have a look. The effect of temperature on KSP and hence solubility using ChemCollective. Brilliant. High scoring. Awesome. Effect of carbon chain length of an ether on strain energy due to torsion and surface and micellar properties. Don't forget, we can have 2 or 3 dependent variables. Might be a little bit ambitious, but we'll see how that one goes. What's the effect of increasing the carbon chain length on the halogenoalkanes on the van der Waals forces and mole enthalpy of formation? High level, right? This is high level. What's the effect of increasing carbon chain length on the van der Waals forces and the enthalpy of formation? So the students are being guided to use WebMo, get some of the data from there, augment it, contextualize it using John Chewies' site, plus one other if you can, do some calculations. If you're doing energetics, then do some calculations using the data booklet, enthalpy formation, combustion, average bond enthalpies. Beautiful data treatment, no question, high level. The final 2 avenues open to us when we are stuck at home or not having access to a laboratory, I would suggest strongly using either ChemReacts, which is this one here. The video of how to use this and how that can be made to be useful is on my channel. Look at successful simulations ChemReacts. The second one is ChemCollective. Have a look at that one. I particularly guide students to use the solubility of salts or solubility product, which produces beautiful data like this. Here's the screenshots. Here's the calculations for KSP. KSP is great. Why is it great? Because it's not on the IB syllabus. That's why it's going to be high scoring. There's personal engagement, exploration, job done. And we also can think about the web.mst.edu, which doesn't roll off the tongue very well, but that's this one here. And if you look at I think it's the University of Missouri Rolla, if you look at their site, they have a number of wonderful simulations which you can use. And it really is realistic, and you can start and you can change the initial concentrations, you can change the temperatures, and the student gets to watch a flask, hopefully, which will go black when the iodine is in excess, and they get to stop the timer. So they do it 3 times, and then therefore they have the uncertainty of their measurement. Thank you very much. Bang on time. So simulations are great. Don't waste your time with VET, RSC, Virtual Labs, Chem in Context. Great for teaching. Don't waste your time. There's no way you get the uncertainty from those, and that's the golden key to success at higher level scoring internal assessments. Modelling, we've seen WebMo. WebMo can be used for teaching and for internal assessments. When it runs out of time, you can use Chem Compute. MolView is also great. You do need to have some great spreadsheet skills. I do find my students often put me to shame that they often have better spreadsheet skills than I would have. But certainly WebMo is key for success in high scoring IAs. I'll show you a high scoring database IA shortly, but just keep those in mind while you are doing your exploration. This student was happy for me to share this. I think I've shared it before, but just to remind you what a decent IA looks like. This was a level 7, 20 plus. I'm not going to give you the actual score, 23. That this came through as, what can we see? We can see lots of references throughout the text. I can see chemistry. I can see chemistry not on the syllabus. Not necessary, but it does help. I can see an explanation using the chemistry that the student has learned. There's a very familiar hydrogen bonding. Here is the 2 research questions. Yes, for secondary you can have 2, or you can have 2 or 3 dependent variables. What are the variable choices? The variables were chosen because of the range of the independent variable and the range of the dependent variable, as Kathleen Quinn says. She then explained the log of the P, polar surface area, hydrogen bond donors and acceptors. The method is what I chose for my internal assessment, what I didn't choose, why I chose those sources, why I chose that range. Clearly, we didn't do the experiments. She's found 3 different sources for the same data, consistent decimal places, nice tabulation, not hugely sophisticated just yet, but just wait and see. Comments throughout, reflection throughout the internal assessment is key. Okay, reasonable graph, got the R² value, okay. Talked about the uncertainties. I don't see any waffle. There is no filler in here. This is either discussion of the numbers or discussion of the chemistry. She's propagated her data. She's propagated her uncertainties. Those horrible lines on there are mine, not hers, when I was talking, doing a lecture on using this one. More chemistry, more data processing, more graphing, continuous data, beautiful, terrible fit, but beautiful data. She then goes on to her evaluation, talks about the limitation, the impact, and the suggestions for improvement. 1, 2, 3, 4. I'd expect about 6, but okay, we can let her have that one. Suggestions for extension and a reasonable conclusion, and then look at the bibliography at the bottom. Beautiful. That's how you do it. People have spoken about my channel, bless them. Here we are. We have some lovely comments from Richard Thornley, from Jeff Muse, and from schools that I have been working with as a workshop leader. If you're interested in doing that, please get back to me at mrmforchem@gmail.com. Happily to discuss with you how can best help you and support your journey in successful secondary database internal assessment. Thank you very much for watching. Have a great day. Bye-bye.